If you look at the challenge of carbon, which is one of the great challenges we face today in terms of climate change, the world emits about 25 billion tons of CO2 every year from man-made sources. We've got to be able to get our arms around that problem, capture and store that CO2, and then be able to measure and monitor and verify that it's there. That's the challenge. The largest scale is what's called geologic sequestration or storage, and that's putting CO2 back into the earth, deep into the small pore spaces that are filled with salt water. The bubbles of CO2 are trapped in the small pore spaces.
The International Panel on Climate Change has estimated that by the year 2050, CCS could contribute on a global basis between 15 and 55% of the total greenhouse gas reductions that we're looking for. Technically speaking, CCS is ready to begin deployment today. I'm not saying that it's commercial today. I'm not saying that we're ready to have widespread deployment tomorrow, but on a technical basis, it's ready to begin deployment today at scale. The main things holding up wide deployment of CCS are the lack of an adequate financial incentive and the lack of a clear regulatory framework.
The University of Texas, through the Bureau of Economic Geology, in partnership and funded by the Department of Energy, and as part of the Southeast Southern States Energy Board, Southeast CARB Regional Partnership Project, is leading the experiments on how this is being done. It started with our Frio Brine pilot just northeast of Houston. We're in the middle of one today in Mississippi on the border with Louisiana in partnership with Denbury Resources, industry, the Department of Energy, federal, and the Southeast CARBs and Southern States Energy Board government to conduct the largest brine injection in the United States today. And we've put several 100,000 tons of CO2 in the saltwater leg down dip from the Cranfield oil field. And the injection continues. So this is a different scale of experiment, but it's on the scale that we need to begin to go towards if we're going to successfully be able to capture and store CO2. A large coal-fired power plant, 1,000 megawatt, may put out 4 to 6 million tons of CO2 every year. So this is the scale of injection that has to happen safely, affordably, and permanently for CO2 sequestration to be successful. We're really happy to be at the university and the Bureau of Economic Geology to be part of that kind of an integrated academic industry government team. The partnerships like that are critical for the future.
Texas is the world's leader in knowing how to inject CO2 and knowing how to understand what happens to CO2 once it's injected underground. Our oil producers have been injecting 30 million tons a year of CO2 for over 30 years. In addition, Texas is blessed with a very large number of oil reservoirs that are suitable for CO2 tertiary recovery. The Bureau of Economic Geology has identified over 500 reservoirs suitable for enhanced oil recovery, or EOR, outside of the Permian Basin, that is, outside of the area that we've traditionally had CO2 floods. These 500 or so reservoirs have over 2.8 billion barrels of oil in recoverable reserves that could be recovered right now at current prices and with current technology. In addition to its oil reservoirs, the state of Texas is blessed with a large number of deep brine formations. The Gulf Coast is arguably the best part of the whole United States for sequestration in brine formations.